Hello again. Welcome back to Grade 10 Applied Math here with Mr. Stone. So here we are looking at now a little shifting gears. We're going to do a little bit of measurement. We're looking at Unit 3, Activity 9, which is calculating surface areas and volumes. Now, we did this a whole bunch in Grade 9. We're just going to do a couple little extension problems. So remember, volume is looking at all the stuff inside of a geometric three-dimensional shape, right? So the volume is all the stuff on the inside of here. And we have these formulas. I'm going to give you all these formulas to calculate them, right? And we hopefully you did a bunch of these in grade 9. We're also going to look, though, at surface area. And these have similar formulas. They can be a little bit more complicated or less complicated, but it basically just means all the stuff on the outside. So the surface area. Like if I tried to make this material or this shape, out of paper, let's say, how much paper would I need? Or if I wanted to cover these things in cloth, how much cloth would I need? Right. So let's try some problems. Right. That's all I'm going to do. I'm going to do 4 problems basically, and that's what our assignment looks like as well. Let's say you've got Frank. He wants to determine the volume of a gold ring, and he's going to do this with what we call displacement. He has a container of water here that is 5 by 6 from the base, and he's got 8 centimeters of water. He puts the ring into the water, and the depth of the water has increased by 0.25 centimeters. So it's gone from 8 centimeters to 8.25 centimeters once he puts the ring in. What is the volume of the ring? So the ring has pushed the water out of the way, it's displaced it, and the change in the volume, or the height here basically, will tell us the volume of the ring. So the volume of water that was displaced is this area that I've highlighted here. It's 5 by 6 by 0.25. And this is a rectangular prism, right? That's what we call this, a three-dimensional shape that's based on a rectangle. And the way that we calculate the volume of a rectangular prism is length times width times height, right? Just all 3 of them just multiplied. So let's plug those numbers in. 5 centimeters times 6 centimeters times 0.25 centimeters gives us an answer of 7.5. Now this is important, centimeters cubed, right? I had 1, 2, 3 centimeters, so my answer is centimeters cubed. And because this was a word problem, always word answers, right? So the ring has a volume of, oh, 1 second. Sorry. So the ring has a volume of 7.5 centimeters cubed. All right, and that's it. We're done. Okay, we figured out the shape that it is. I'm going to give you a formula sheet, so you look on the formula sheet, find out what it is. You write out the formula, you plug in, solve, and a final statement. Okay, and we're good to go. Let's try another one. Oh, no, sorry. Second half of this problem. We know the volume, 7.5 centimeters. If the cost of gold is $250 for a centimeter cubed, a lot of money. You have to think about a centimeter by a centimeter by a centimeter cube. How much does the ring cost? We know that it was 7.5 centimeters cubed. So to find the cost, we're going to multiply the volume that we calculated times the cost per one volume. So $250 per centimeters cubed. And that's going to give us a cost of $1,875. Wow, it's a big ring. So the cost of the ring is $1,875. Again, remember, we had a word problem, so we end up with a word solution. Okay? All right, let's try another one. Spheres now. So we have a huge water balloon. We're going to fill it with water until it is 3 feet across. Okay, 3 foot across water balloon. Water weighs 6.3 pounds per cubic foot. If you have a foot by foot by foot cube, that's going to weigh 6.3 pounds. How much does this massive 3 foot across water balloon weigh? So first thing we have to do is we have to calculate the volume of our water balloon, to calculate how much water we use to fill it up with. And the tricky thing here is it doesn't give us the radius. It only gives us the diameter. Remember, diameter is, right now, this length across of here is called the diameter. Sorry, diameter. But our formula is 4/3 pi r cubed, which is an r in it, which is the radius. So we need the radius, which is going to be half the diameter. So if my diameter is 3 feet, my radius is going to be 1.5 feet. So I look on my formula sheet. It says that the volume of a sphere is 4 divided by 3. So this number 1.333 repeating, times pi. Remember, pi is a very special number. We can approximate it as 3.14. But remember that pi is the ratio of a circle's circumference divided by its diameter. Another way you can think about it is, if I have a circle and let's say I want to walk across it and it's 1 meter across, that means that I need to walk around the circle, all the way around the circumference of the circle is going to be 3.14 or pi meters across. Or not across, pi meters all around. It's how much bigger a circle is defined by the fact that if you walk around it, it's always a little bit more than 3 times more to walk around it than to walk across it. That's what pi is. 3.14 is how much farther it is to walk around a circle than across a circle. That's what pi means, okay? So that's that number pi here, Greek letter for letter P, and multiply by r cubed. So the only thing we need to know in this case, the only unknown in this formula is the radius. So we know the radius is 1.5. I'm going to plug that in. Now, be careful here. Remember bed mass. What does bed mass stand for? Remember, brackets, brackets, exponents, division, multiplication, addition, subtraction. So exponents comes before multiplication. So we have to do this first. So let's cube 1.5. So 1.5 times 1.5 times 1.5, or in your calculator 1.5. There's maybe you have a cube button, maybe you have like a little hat, and then hit a 3 after that, something like that. Depends on how your calculator works. But we're going to cube it. Or if you're stuck on that, just multiply 1.5 times 1.5 times 1.5. And then we're going to do the multiplication. So 4 divided by 3 times 3.14 times 3.375. So this fraction here might mess you up. So just on your calculator, you can just type in 4 divided, right? That's what that symbol kind of means. 4 divided by 3 times pi times 3.375 gives us a final answer of 14.35 feet cubed. So this 3 foot across water balloon is almost 14 cubic feet of water. That's a lot of water. And the question is, how much does it weigh? Right, that was the first part of our problem. To find out the weight, we're going to have to first calculate the volume, and then I'm going to multiply my volume times the weight per 1 cubic foot. And that's going to give me a final answer of 89 pounds. Wow. So a water balloon that is 3 feet across weighs nearly 100 pounds. All right. And again, word problem, final answer in words. The water balloon weighs 89 pounds. And we're finished. Okay? The second part of the question asks us, what's the surface area? How much material is the water balloon made out of? What's the skin of the water balloon? How much rubber are we using? And the formula for the surface area of a sphere is 4 times pi times r squared this time. So we're going to put in our numbers. Again, remember to do the exponent first. That's going to give us 2.25. Then we just multiply those out, and we end up with a square footage of 28 square feet. That's a lot. So a water balloon that is 3 feet across has a surface area of a little bit more than 28 square feet. Okay, the water balloon has a surface area of 28.26 feet squared. And we're finished. All right. So if you want to calculate the surface area, go to your surface area formulas. All these formulas are on the sheet that's on D2L. I'll also add it in the description of the video, and I'll add it to Teams as well. All right, let's try a little bit harder one. Let's say I'm giving you the volume. Let's say I have a Pringles can, telling you that the volume of a Pringles can is 850 cubic centimeters. That's the volume of it. The radius is 3 centimeters. How tall is the can? What's the height of the can? So this question is a little bit backwards. Previously, I'd given you all the information. You just have to calculate the volume. What if I give you the volume and you're asked to find one of the dimensions? So we look on our formula sheet. We find that the volume of a cylinder is pi r squared. So pi r squared is just the area of the base. Let's say this is a bottom here. It's a circle. So that's the area of a circle multiplied by h. Now, if I substitute in what I know, right, I know that 800 is the volume, pi is 3.14, r is 3 squared. I'm left with h, the unknown, over here. I'm going to have to do a little bit of algebra. So I square my 3, and I do the exponent first, then I multiply. So I end up with 850 is equal to 28.26 times h. So my height is something multiplied by 28.26 that gives me 850. Right? That's what that means. H is the number that when I multiply it by 28.26 gives me 850. So to solve this, right, it's multiplying, right? So to solve it, I do the opposite. So I divide both sides by 28.28. So these cancel, and I'm left with H is 30 centimeters. That makes sense, right? Another awesome thing about geometry, right, or all these measurement things, you can think about it. Is a Pringles can about 30 centimeters? Yeah, that makes sense. So the Pringles can is 30 centimeters tall. And we're done. All right, so again, formula, substitute, algebra, statement. That's how we do all these problems. All right, one last one. A little bit big problem, kind of scary looking. So this is not a nice shape. All right, this is not one of the ones on our formula sheet. Right, we don't have a pentagonal prism on our formula sheet. That's a pentagon, right? 1, 2, 3, 4, 5. Yeah, it's a pentagon, so it's a pentagonal prism. But they want us to find the volume of this swimming pool. Now, what's nice about this is this shape basically has like this shape on the front is the same shape as the one at the back. So once we calculate the area of the front face, so once you get the area, let's say, of this front piece, and you multiply it by the depth, right? This all these lines here are all 4, right? It's we take that base and we stretch it out by 4 meters. If you multiply it by 4, that'll give you the volume. So really, this question is just asking you calculate the area of that front face of this pentagon. Again, to calculate the volume of complex shapes, let's say we have this weird shape like this, and I have another weird shape like this. The same shape. Just don't look the same, do they? Let's try this again. Let's say I have this weird shape like this, and the same thing on the bottom, on the top and the bottom, and the whole thing is just extended, right? This is my weird shape. Got like weird kidney bean on top and bottom. If I can find the area of just the bottom or the top, one of the faces, if I multiply it by the height, that's my volume. Whatever the area is on the bottom multiplied by the height, that gives me the total volume. Sorry, whatever the area is on the bottom. So really, all this question is asking you is what is the area of the front face? You multiply that area times the depth, and that'll give you the volume. So we're really looking for the volume of this guy. Sorry, I said the word again. We're looking for the area of that. So to do that, let's do a little bit of composite shapes, what you probably did in grade 9. So I take this weird looking thing, and I notice that it kind of looks like a rectangle that's had a triangle chopped out of it, right? And because I know the lengths, I know this was 6, and I know that this piece is 2, the extra piece that I cut out has to be 4, right? Because 2 plus 4 is 6. And since I know that the longer side here is 3, the shorter one's 2, the extra has to be 1, right? Because 2 plus 1 is 3, right? These two have to be the same. The lengths and the widths have to be the same. So really, I have a larger rectangle that's 6 by 3. Subtract this smaller triangle that's 4 by 1. So to find my total area, I'm just going to take A2, A1, sorry, the bigger one, and subtract A2. So let's calculate A1. That's just length times width, right? It's a rectangle. So length times width, 6 times 3. So the bigger rectangle is 18 meters squared. My triangle is going to be base times height divided by 2. That's going to be 4 times 1 divided by 2. 4 times 1 is 4. 4 divided by 2, that's just 2 meters squared. And to get my total area, right, this thing here, this is called a total, right, all this stuff here, that's going to be the bigger area, A1, subtract the smaller area, A2, which is just 18 subtract 2, or 16. So my area of that pentagon, that weird front face, is going to be 16 meters squared. And now that I have that, to calculate my total volume, it's just going to be that front area times the height, or in this case, sort of the depth, this way. You can call that depth if you want. So that's just going to be the answer from my previous slide, which was 16 meters squared times 4, right? Because I've gone 4 meters in this direction everywhere. Sort of taken that triangle, that pentagon, and sort of stretched it into the page 4 meters. So I get a final answer of 64 meters cubed. Notice here I had meters squared and meters. So this is meters to the 1. So I have 2 meters here. I have another meter here. So I get meters cubed. I have 3 of them all together. 16 times 4 is 64. Meters cubed, sorry, meters squared times meters is meters cubed. The volume is always going to be in either meters cubed or centimeters cubed or something cubed, feet cubed. Area is always squared. And last thing we always have to do, the volume of the pool is 64 meters cubed. All right? Okay, so that was a big problem. That was kind of a scary problem, right? So what did we do? Let's go back. We took our shape. We noticed it was strange. But we noticed that there was the same face on the front and on the back. So we're calculating the area of the front face. I take my area of my front face, notice that it's actually 2 different areas subtracted. And then I calculate the areas, subtract them, get a total, multiply by the depth, and I get a final answer of 64 meters cubed. And finished. All right, so this lesson was just me basically doing a bunch of these problems. I did 4 of them all together. If you get stuck on any of them, go back. This one is very similar to the one of the ones on assignment. So if you stuck around to the end of the video, good job, and this will help you a lot. All right, okay, so best of luck, and we're almost done the course. All right, we're almost finished. And with that, talk to you later. Take care, guys.